All right, if you're a medicine or biology student, you're going to want to pay close attention. We're about to dive into one of the most critical topics you will ever study: antibiotics. I mean, these are our primary weapons in the constant war against bacteria, and truly understanding them, it's completely non negotiable for a career in medicine. So let's get right into it.
So here's our game plan. We're going to break this down into 4 key sections. First up, the fundamentals. Got to know the basic rules of engagement, right? Then we'll open up the antibiotic arsenal and see what we're working with. After that, we'll talk strategy. How do we choose the right weapon for the job? And finally, we'll tackle the biggest challenge on the horizon, the rise of resistance.
Okay, let's jump in. Before we can even begin to talk strategy or pick our weapons, we all need to be speaking the same language. This first part is all about defining our terms, getting that foundational vocabulary down, because everything else builds on this. First things first, the star of the show, antibiotics. What are they, really? Well, at their core, they're chemical substances with one very specific mission: to either stop microorganisms like bacteria and fungi from growing, or to just kill them outright. It sounds simple, but wow, is it powerful. Now, here's something that trips people up all the time. Antibiotics are actually part of a much bigger category called chemotherapeutic agents. Think of it like this. Chemotherapeutic agents is the entire army. And in that army, you have specialized units like antivirals, antifungals, and of course, our guys, the antibiotics. So just remember, all antibiotics are chemotherapeutic agents, but not all chemotherapeutic agents are antibiotics. So this is absolutely crucial. We need to understand how these agents actually fight. And there's a huge distinction here. A microbicidal agent, and you can hear the cidal part in there, like homicidal, is lethal. It flat out kills the microorganisms. A microbiostatic agent, on the other hand, just stops them in their tracks. It inhibits their growth, keeps them from multiplying, and basically gives your body's own immune system a fighting chance to come in and clear them out. All right, now that we've got our terms defined, it is time to open up the armory. In this next section, we're going to explore the incredible antibiotic arsenal we have, and more importantly, how we classify all these different weapons to really understand their strengths and their weaknesses. You know, our modern arsenal has a pretty famous origin story. It all starts back in 1928 with Alexander Fleming. His accidental discovery of penicillin wasn't just some neat scientific breakthrough. It completely changed the game. It revolutionized medicine and gave us our first true superweapon against bacterial infections. So, with literally hundreds of antibiotics out there, how do we make sense of it all? Well, we've got a pretty clear blueprint for classifying them. We group them in 3 main ways: by their chemical structure, by their spectrum of action, and, what I think is most important, their mechanism of action. In other words, how do they actually attack the bacteria? Let's start with that first major mechanism: inhibiting cell wall synthesis. See, bacteria have this rigid cell wall that protects them. Antibiotics, like penicillins and cephalosporins, are designed to target that wall and break it down. It's kind of like demolishing the walls of an enemy fortress. The whole thing just collapses, and the bacterium is destroyed. Okay, strategy number 2 is to go after the bacteria's production lines. Drugs like tetracyclines and macrolides, they target the bacterial ribosomes. You can think of ribosomes as these tiny factories that churn out essential proteins. So by shutting down these factories, the antibiotic basically starves the bacterium of everything it needs to survive and replicate. And a third key mechanism is a direct hit on the enemy's command center. This method, used by quinolones and rifamycins, stops the bacteria from copying its DNA or creating RNA. What does that mean? Well, it means it can't reproduce. You're effectively stopping the enemy army from creating any new soldiers. Now, besides how they attack, we also classify antibiotics by their spectrum. A narrow-spectrum antibiotic is like a sniper rifle. It's super precise, targeting only a few specific types of bacteria. On the flip side, a broad-spectrum antibiotic is more like a shotgun. It's effective against a whole wide range of bacteria, and each one has its own strategic use for sure. So, this all brings us to the really practical side of things. We've got this massive arsenal at our disposal. But how do clinicians actually form a battle plan? How do they look at a specific infection in a specific patient and choose the single best weapon? Well, it's a really complex calculation. A doctor has to consider the type of infection, of course, but also the specific germ's sensitivity.
They're weighing the patient's overall health, they're checking for any allergies, and they have to balance the drug's effectiveness against any potential side effects and even its cost. It is a true strategic assessment every single time.
So how do we figure out a pathogen sensitivity? Well, one of the most common lab tests is the Kirby-Bauer method. A sample of the bacteria from the patient is spread all over an agar plate. Then you place these little paper discs on top, and each one is soaked in a different antibiotic. You let it incubate, and if an antibiotic works, you'll see this clear ring around the disc where no bacteria could grow. That clear ring, that's what we call the zone of inhibition. The results from tests like the Kirby-Bauer get compiled into this super important document called an antibiogram. You should think of this as the intelligence report coming back from the front lines. It tells the doctor exactly which antibiotics that specific bug is sensitive to and which ones it's resistant to. It's what guides them to the most effective choice. And for even more precision, labs can determine the MIC, which stands for minimum inhibitory concentration. This tells us the absolute lowest dose of an antibiotic that's needed to stop the bacteria from growing. And the goal here is critical. You want to use just enough power to win the battle, but not so much that you cause unnecessary side effects or worse, help create resistance. Okay, time for our final section, because for every action, there is a reaction. For decades, we've been waging this war, but you know what? The enemy is adapting. And this is, without a doubt, the single greatest challenge in modern infectious disease, the rise of antibiotic resistance. So what is resistance exactly? It's when bacteria, just through sheer evolution, develop the ability to survive an attack from an antibiotic that used to be lethal to them. They literally learn how to defeat our best weapons, which makes them useless, and that makes infections way harder and sometimes even impossible to treat. Now, resistance shows up in two main forms. Some bacteria just have a natural resistance. They were basically born with a built-in defense against certain antibiotics. The one we're really worried about, though, is acquired resistance. This is a defense that's learned on the battlefield, where bacteria gain resistance either through a random genetic mutation or by sharing resistance genes with each other. And believe it or not, it gets even more complicated. There's something called cross-resistance. This is where a bacterium's new defense against one antibiotic also protects it from other similar antibiotics in the same chemical family, even ones it has never, ever seen before. It's like developing a shield that suddenly works against swords, spears, and arrows all at once. Which, of course, leaves us with the critical question for the entire future of medicine. This is an evolutionary arms race, plain and simple. Bacteria are constantly evolving new defenses, and we are racing to develop new weapons. So as we look to the future, the ultimate question really is, can our antibiotic arsenal keep up?